Hello class, these are our notes for Calc AB. Today we are looking at trigonometric integrals. So we did a bunch of stuff with trig integrals earlier this year, and I like how we kind of cycled through it. Like first we learned how to do derivatives for trig, and then we did integrals for trig, and then we did integrals that were a little more complicated where they had exponents. And now we're looking at ones where not only are they going to have exponents, like we could have cosine cubed and sine to the fourth power of x dx, but we're going to have to use some power reducing trig stuff to be able to work with them. So our goal is really, like before, our goal is to actually just use the power rule. So our goal, let me go ahead and write this down. Goal is to use power rule. And so what I mean by that is we're going to have like some kind of u du, and it might not be u to the first power, but we know when we integrate, we're going to make that like 1/2 u squared plus c. So we increased our exponent divided by the new exponent, but instead u is going to be some kind of trig function. But we could be integrating u squared, or we could be integrating u to the third power, right? So our goal is to use power rule. So that's going to be what power rule is. So first we want to remember some of our trig identities before. So we're going to remember we have Pythagorean identities, and today we're only looking at sine and cosine. So I'm splitting the notes up into two parts. So for Pythagorean identities, I guess it's identity because we're only looking at sine and cosine today. So let's go ahead and switch that. That means we're going to have cosine squared theta, or x, or whatever your variable is, plus sine squared theta is equal to 1. And then for power reducing, and these I think we've used like maybe once or twice this year. So this is going back to pre-calc. So power reducing, if we have sine squared theta, that's going to be 1 minus cosine of 2 theta over 2. So it changes from sine to cosine, right? I no longer have any squared, but my angle's doubling, and there's a minus sign there. That's the really big important part. And then if I have cosine squared theta, that's going to be 1 plus cosine 2 theta over 2. So if it's sine, I have a minus. If it's cosine, it's plus. Either way, I'm doubling the angle. So our basic guidelines here, if you remember from before, we're basically going to want to, if there's odd, we're going to want to change the odd power 1, but we have to save a factor. So use odd power let's say as for your du, change, or actually, how do I want to write that? Like we're going to save one factor of it basically and change the rest. So save one factor and change the rest. So that means we're going to be either changing it to, if it's in sine already, like if we have sine cubed, then we're going to save a factor of sine x to be our du. The rest of it would be converted to cosine, right? So we're going to convert to the other trig function. If only even, then power reducing. I think it'll make more sense once we start working. And I'll kind of talk you through my logic on each of these. All right. So let's go ahead and look at this. So if I have sine cubed, right, that's my one that's odd. So I'm going to be taking that sine cubed and I'm going to be making it sine squared x times an extra sine x times cosine to the fourth x dx. And so this is the guy I'm going to save as a du. So my u is going to be cosine x. Derivative of cosine is going to be a negative sine x dx. So like this guy, I'm going to convert to cosine. So I'm going to change to cosine x. And then this one, I'm going to save for my du. And because I'm converting this one to cosine x, I already have some cosine x there. They're all going to go together. So let's go ahead and use our Pythagorean identity here. I wouldn't want to do power reducing if I can do Pythagorean. It's only squared. So sine squared x is going to be 1 minus cosine squared x. And then I'm going to write the cosine to the fourth power x, and then times my sine x dx. So like this part, the sine x dx part is going to be where I get my du from. I'm going to have to worry about the negative at some point. And then I'm noticing here, like this is kind of a mess. I'm going to distribute cosine to the fourth power of x. It's really cosine of x to the fourth power, right? So this is going to be cosine for x minus, when I multiply these two together, now I'm going to be up to cosine 6x. So cosine x to the sixth power. And then I'm going to split this up into two integrals. So we're going to have cosine 4x sine x dx minus cosine 6x. It's not a 6x though, right? It's cosine of x raised to the sixth power. I'm being kind of sloppy with the way I'm saying it. Sine x dx. I know I need to have negatives for my du. So let's go ahead and put a negative out front. So now I have like my u to the fourth, and this is my du over here. And then I already have a minus here, so I'm going to make it plus, so just basically move that negative sign to the middle of this. So I have that negative sine x that I need for my du. And this one is basically like u to the sixth. So now I've got my power rule. So I would have negative if I'm increasing. My exponent here, it was fourth power, now it's going to be fifth power, but I'm dividing by 5. So negative 1/5 cosine of x raised to the fifth power. So I'm writing cosine to the fifth power x because that's my shorthand, right? That really means cosine x raised to the fifth power. Those are equivalent. And then I would have a plus sign over here. And then this is going to be 1/7. And then, of course, plus c. So this is kind of what we did before. I think this is a more complicated one, but we did problems a lot like this earlier this year. I couldn't tell you what chapter it was, but we have done problems like this, and they were tough. I want to erase this because I didn't do the whole thing, so I want to make sure it looks equivalent. So on the next one, this looks like a mess. So I see a couple issues here. And the first issue is that I have my sine inside that square root. My sine x is inside there. So I can't really do anything with the sine x because it's inside. Like the square root is kind of a mess. So I want to make a little note of that. Can't do anything with the square root. And also this one is my odd power, right? So it makes sense here because I've already got sine that I'm stuck with inside that square root to try to save a factor of cosine. So save a factor of cosine x for the du and change everything else to sine. And this is a definite integral. So I know you're thinking like, hey, I could just put that to my calculator, but remember, most of your AP test is not going to have a calculator. So we need to be able to do this stuff. So we're going to end up letting u equal our sine x, which means our du will be cosine x. So the first thing I notice here is I want to rewrite this. So from pi over 6 to pi over 3. And I'm going to make it cosine squared x. And then I've got my extra cosine x dx over here. Remember, this guy's just hanging out because that's going to be my du. And then we're going to use our Pythagorean identity for our cosine x because it's just squared. If it was a bigger power, I would have to use power reducing, right? But I don't have to. For squared, it's pretty easy. We'll look at a power reducing one next. So now I could write this as 1 minus sine squared x. And then we're going to split this up into two integrals because I have the 1 minus sine squared. So I'm going to have the one integral with 1. The other one is sine squared. So let's go ahead and do that. So let's see. We'll have 1 over square root of sine x times cosine x dx minus, and then our second integral is going to be sine squared x over square root of sine x times cosine x dx. Okay, so now this is where it gets really cool because I'm looking at the sine squared x over square root of sine x, and I'm thinking about how this is really sine x to the second power over sine x to the 1/2 power. And since they both have sine x, just raised to different powers, I can actually subtract those exponents. So that's going to make that easy to work with. And the first one, it's really just like 1 over my square root. So I think I'm going to write that as sine x to the negative 1/2 power. And then I've got my cosine x dx. Okay, so I like to integrate everything at once. So I'm just going to rewrite my first one because this one's really all set. It's really like a u to the negative 1/2 power, and here's my du. I don't really want to make a u substitution here because I've got these bounds and I don't think I really want to convert them to u's, so I'm going to leave them that way. So let's see, sine x. They might be easy to convert. They might not be. I haven't looked at it. I just feel like it's not really necessary for me to do a full-on u substitution. The second one, 2 minus 1/2 is going to be 1/2, so that's going to be a 3/2 power. So over here, I've got sine of x to the 3/2 power times my du part of it. Okay, so now I can go ahead and integrate. This is great. So I need to add 1 to my negative 1/2. So my new power is 1/2, and then I have to divide by 1/2. And so that means multiply by 2. So I'm going to have 2 times that sine x. And then remember, this is going from pi over 6 to pi over 3. Oh, but my new power is 1/2. I can't forget about that. It's kind of bad. This is it's not a great, I don't really want to evaluate that. The second one, if I have 3/2 right now and I add 1, it's 5/2. So if I divide by 5/2, I'm multiplying by 2/5. So sine x to the 5/2 power from pi over 6 to pi over 3. Wow. So I'm going to have to evaluate pi over 3 and pi over 6. So let's see, this is going to be 2 times sine of pi over 3 to the 1/2 minus sine of pi over 6 to the 1/2 power. So again, I'm going to have to draw those out, and then we'll have 2/5 sine of pi over 3 to the 5/2 minus sine of pi over 6 to the 5/2 power. Okay, it's getting pretty ugly. So let's go ahead and figure out those trig, what those are going to be. So pi over 3, that's when my 1 is down here. This is my root 3, 2. So this guy is going to be root 3 over 2. And then my other one, pi over 6, is going to be 1/2. All right, so sine of pi over 3, I already said was root 3 over 2. So that's going to be to the 1/2 power. minus, yeah, it's a square root of a square root, not real pretty. And then over here I have 1/2 to the 1/2 power. That's not super terrible. Minus 2/5. Sine pi over 3. Again, that's going to be root 3 over 2 to the 5/2 power. So this is about when I gave up earlier and said, I'm going to grab a calculator. So I did grab a calculator. And I went ahead and cranked that out so you didn't have to stop in the middle of the video and wait for me. I got this was approximately 0.239. So remember, for College Board, it's always going to be 3 decimal places. If we were evaluating this by hand and it was not a calculator thing, remember you can stop. You could stop like right here and say, this is my answer. So we always have that as an option too. This is more just us practicing trig, right? That's really what we're trying to do here. And we're trying to do as much as we possibly can, because working on this trig, when we do really difficult things, the easy things become easier. So I guess we could have even stopped it earlier than that. We could have done the whole thing on a calculator, right? But we're trying to just exercise our trig right now. So for the last one, I only have even. So if I only have even, then I need to do power reducing. So again, I'm really trying to make sure I'm explaining my thinking for all of these. And my power reducing formula for cosine, remember cosine's the plus one. So I have cosine squared theta equals 1 plus cosine 2 theta over 2. So the problem here is I have fourth power, but my formula is for squared. So the first thing I'm going to do is I'm going to rewrite this as cosine squared x and then square it. And now for my cosine squared x, right, for this part of it, I can go ahead and use my power reducing formula. So I'm going to go ahead and write 1 plus cosine, remember it doubles the angle, 2x, and then it's all over 2, but this is still squared. So when I square my numerator, 1 squared is 1. Remember, to get my middle term, I'm multiplying 1 times cosine 2x, which is cosine 2x, but then I'm doubling it. So it's going to be 2 cosine 2x. And then my last term squared would be cosine squared 2x, which is really cosine of 2x and then the whole thing squared. My denominator I have to square as well. That's going to be 4. So at this point, you can see we're going to have to do power reducing again. So I can factor out a 1/4 from everything. And then my next job is going to be applying the power rule one more time to my cosine squared 2x. So this is what I have right now. So I'm going to break up these integrals, and I'm going to take care of the cosine squared 2x by power reduce again. So let's go ahead and write down right now I have a 1/4 of just 1 dx, which is just 1/4 integral dx, 1/4 of the integral 2 cosine 2x dx plus 1/4 integral cosine squared 2x dx, and then let's make a little note here, power reduce again. All right. And I know it's weird to have the 2 here. I could make that a 1/2, but I'm recognizing if my u is 2x, my du is going to be 2 dx. So I'm going to need the 2 there anyway. So there's no point in factoring it out. So 1/4, I'm not going to write the 1. I am going to go ahead and rewrite this as cosine 2x times 2 dx. And then here I want to do my power reducing. So this is going to be 1 plus, and it doubles the angle again. So now it's going to be cosine 4x all over 2. So the 2 and the 4 could multiply. I want to integrate everything at once. You wouldn't have to. I just like doing it all at once. But you could just go ahead and integrate if you didn't want to keep writing those integrals over and over again. So when we break this one apart, let's see, this is going to be a 1/8 times 1 plus cosine, doing lots of steps here, probably more than what I need to. So now this I want to break up into 2 integrals again. So rewriting the first two. And I'm going to have a 1/8 dx plus a 1/8 of cosine 4x dx. Almost forgot my integral symbol. I can go ahead and combine these two guys together. 1/4 plus 1/8 is going to be 3/8. My dogs are going crazy. I have no idea what's going on at my house. But I'm so close to being done with this video, we're not stopping right now. Oops, forgot that dx. Oh, it wasn't a 2x, it's a 2dx. I bet that was driving you guys crazy. So let's go ahead and fix that. All right, so let's see, 2dx, 2dx. And now this one, if I want to have a 4, I want to sneak a 4 in here, then this is going to have to be multiplied by a 1/4. So 1/32 integral of cosine 4x times 4 dx. Okay, now we're finally ready to integrate. So when we integrate 3/8, we just have 3/8 x. When we integrate this middle one, remember when we integrate cosine, it just becomes sine, right? So this is going to be 1/4, and this is like cosine u and then du. So it's just going to be sine 2x. So that's good to go, and then plus 1/32 of sine 4x, and then plus c. If you have trouble remembering signs, remember you could always go back and say, well, if my y equals sine x, my y prime equals a positive cosine x, right? And that's going to help you when you're moving backwards from cosine to sine. Just being accurate with your plus and minuses here. So we are all set. We integrated this. And that was just an example of power reducing. So last is we have a couple of cool formulas here, and then we'll do part 2 notes in a little bit. I'll have to come back and do a different video, see how my family's doing. So Wallace's formula, so this is for a definite integral, but this is really, really cool. So if I have some power of cosine and I want to know my integral from 0 to pi over 2, so I have two different formulas, one odd, one even. It shows that we can like multiply all these fractions up to n. So like let's say I was doing the integral, so this is like a way to get definite integrals, but like a quick and dirty way. So if I'm integrating from 0 to pi over 2, say I have cosine 8th power, so cosine x the 8th power dx, then I'm going to keep multiply fractions until I get up to 8 minus 1 over 8. So 8 minus 1 over 8 would be 7/8. So you can see these fractions like there's a pattern, right? 2, 3, 4, 5, 6, 7. So you keep going until, oh shoot, this is the odd pattern. So this one wouldn't work for that one. This one's going to work for, say, 9. So let's do our 9th power. So we would go up to 9 minus 1 over 9. So we go up to 8/9. So we would have 2/3 times 4/5 times 6/7 times 8/9. So that's that pattern, right? After 8/9, if I did 11th power, right, it would be 10/11. So the numbers 2, 3, 4, 5, 6, 7, 8, 9 just kind of go in order. And then the other one is for even instead, and that one has a pi over 2 in it, and the numbers have like the same kind of pattern. So this is just a pretty cool thing to know. It's really interesting to think about, like, how did someone come up with this? How did they find this pattern in the first place? So today is all about trig integrals. Basically, our strategy is to keep the even stuff, change the odd stuff, but save a factor for our du. We might have to do power reducing. We might have some square roots. We might have to break apart fractions, right? So all kinds of interesting stuff going on. The last one was definitely our example of power reducing. Today we focused on sine and cosine. When I do my second video, it'll be secant and tangent. So as always, if you need help, please make sure that you ask.